Welcome back, students. We are finally here. We are going to begin to address the question of where the electron is in the hydrogen atom. So now that we have formulated the Schrödinger equation for translational, vibrational, and rotational degrees of freedom and solved the eigenfunctions solutions for these total energy operators, we can use what we've done so far and put this together to figure out and solve the problem that's most interesting to us as chemists, that of the hydrogen atom and where the electron is in that atom. Recall that our previous model of the atom that we've been using so far was formulated by Bohr, and Bohr posited that electrons orbit the nucleus at discrete radii. This model is able to correctly predict the quantized hydrogen emission spectrum and give an explanation for why the electrons can exist outside the nucleus. However, note that it clashes with Heisenberg's uncertainty principle. Under Bohr's model, we know that the electron's energy and we know where the orbit radius is, so we know its position. So Bohr has incorporated the wavelength of the electrons in a way, and it's a good enough way to get quantization correct, but it doesn't quite address how we should do this. And so we're going to do this with the Schrödinger equation now. So we'll be talking about the hydrogen atom today. We'll set this up and we'll get the solutions. And then next time we will look at what we can do with the solutions. So the learning goals for today are going to be to use the Schrödinger's equation to find the eigenfunctions for the electron orbiting the nucleus, just like we had before for our previous models. We'll now want to be pretty comfortable working with spherical coordinates because as we talk about the orbitals, they're obviously spherical in some way. We'll describe the hydrogen atom orbitals mathematically. And we'll, of course, want to be able to compare the complex formulations of these functions and real solutions that are easier for us to visualize. So we have the Bohr model. I mentioned that earlier, but I mentioned as well that this clashes with Heisenberg's uncertainty principle. So since we can't know the position and the energy of the electron simultaneously, and we do know the energy because we can measure it with something like that hydrogen atom emission spectrum, we shouldn't be able to know its position. And what we want to do then is not describe the electron as some particle with a wavelength, but rather use the electron, describe it as a wave using Schrödinger's wave equation. And so the way that we will always go about doing this is by solving the Schrödinger equation. So the first question that we need when solving this equation is to identify what the potential is. And of course, the potential is this Coulombic attraction force between the electron and the nucleus. And we can describe that again using classical physics as the following. So it's negative E squared over 4 pi epsilon naught times R. This 4 pi epsilon naught talks about how charges work in a vacuum. R is the distance between the electron and the nucleus. And here, negative E squared is the charge of the electron, which is negative E, times the charge of the nucleus, which is a single proton, which is positive E. So negative E times positive E gives negative E squared for this potential. So now all we have to do is substitute this into the solution, and we get something like this. Now, what I want you to note here is that I have this, rather than X, I have a tau, where here tau is a shorthand symbol for all of our variables. Now, what are our variables? It's no longer simply a function of X. Right? The electron can be anywhere in a three-dimensional space in regards to the nucleus. So the simplest way to discuss this is using spherical coordinates. We set the nucleus at the point 0, 0, 0, and then we talk about how far the electron is away with the distance r, and then the angles theta and phi, which are the same angles that we used before to talk about rotation. And so when we do this, we get the following equation that maybe looks a little bit nasty. So here we can see again, all this horrible stuff on the inside of this brackets are simply d2 dx2 d2 dy2 plus d2 dz2, but we converted it to spherical coordinates, which will make the problem simpler for ourselves. You have to trust me. And then we have the potential E squared over 4 pi epsilon naught, and then this is equal to our energy, or total energy for the hydrogen atom, times our wave function. So when we have this in hand, the next question is, of course, how do we solve it? Again, the actual solving of this equation is beyond the scope of this class. However, we can make some important observations and simplifications like we did for rotation. So one of the first things we can note is that the potential, which we can see here or here, is only dependent on one of our variables, r. It only matters how far away the electron is from the nucleus. That's how much potential energy it has. And again, for the same kinds of reasons we've been doing this in the past, that means we can achieve a separation of variables. So our function of r, theta, and phi is rather the product of three functions, one that's only a function of r, one that's only a function of theta, and one that's only a function of phi. And so we'll go to the board here and we'll look at what we can do knowing this and keeping these ideas in mind. Okay, so I have our Schrödinger's equation written up here, and I have our separation of variables down here. So what can we do with this big mess? Now, first of all, we're going to simplify this by looking at this angular part of our equation. So if we just consider this angular part and substitute in this change of variables function, we'll end up with the following. I'm going to pool my r functions off to one side and then treat with the rest of them here. So we can't forget this constant's negative h bar squared over 2mr squared. So if I keep these, I'll write here negative r as our function of r over 2me r squared. And then what I have is negative h bar squared times this part on the inside. So to save some time here, I'm just going to copy these and hope this works nice and smoothly. So this is our function on the inside. And what we've done is we're not taking the derivatives of our function of r, theta, and phi. We've already pulled the r components out. So instead we have our theta function of theta and our phi function of phi, and that should go in both places here. Now, why have I done this? Well, when we look at this equation, we have actually seen this before. This looks very much like our total energy operator for the rigid rotor. However, note that there are some differences, right? We have this function of r here, and we want to keep this r outside with it. So that means we don't have negative h bar squared over 2I, we just have negative h bar squared. So this is not the total energy operator for the rigid rotor, but it is something else. So recall that we had an L squared operator that was equal to the total energy operator divided by 2I. So that means that this whole term here can be represented by the L squared operator. So that simplifies this function a great deal. And what we have then is that this whole part here can be simply rewritten as negative r as our function of r times 2me r squared times the L squared operator operating on our functions of theta and phi. And this is nice because we know the results of this. Remember that the L squared operator has eigenfunctions of h bar squared times L plus 1. So if I operate on my functions of theta and phi with the L squared operator, what I return is always h bar squared times, I guess I wrote it this way, times L plus 1, where L is simply a quantum number, and so it's 1, 2, 3, something like that. And then we will, of course, multiply our function still by theta and phi. So with this in mind, we can put this together and come up with a much simpler equation. So what we have after doing this is the following. We have negative h bar squared over 2me r squared times a single derivative with respect to r times r squared times the derivative of our r function with respect to r. And of course, we also have, that is not being operated on by this operator, we have our function of theta and our function of phi. And then in the second term, we return plus h bar squared over 2me r squared L L plus 1. And then we have our function of R, our function of theta, and our function of phi. And then we have our potential term. So we have minus E squared over 4 pi epsilon naught R times our function of R, theta, and phi. And this is all equal to the total energy times our function of R, theta, and phi. And so note then what we can do is say, hey, every single one of these terms has the theta and phi function. So we can eliminate the theta and phi function from all of these terms. And what this shows us is that the total energy does not depend on the angle. It only depends on the radius, the distance from the nucleus. And we can rewrite this again as negative h bar squared over 2me r squared times the derivative with respect to r of r squared times the derivative of our radial function with respect to r. And then we can add in everything else. So we'll have a constant term here that comes from this second term. That's h bar squared L plus 1 over 2me r squared, and then minus e squared over 4 pi epsilon naught r. And these were all multiplied by our radial function r. And then this is simply equal to the energy multiplied by our radial function. And so to solve the Schrödinger equation, we now need to solve this differential equation to get what our radial distribution functions are. So what we have here is actually a potential that is, we can call this whole term in the brackets here a V effective, that's made up of a Coulombic force and a centrifugal force, just like Bohr predicted, that are opposite in sign there. The centrifugal force depends on r to the -2 and dominates at small distances, which explains why electrons do not crash into the nucleus. And this effect is dependent on L. The larger L is, the further away the electron is on average. So at this point, we have simplified the initial Schrödinger equation that we set up and are now left with an equation that only depends on the distance r. And we haven't really lost the theta and phi components here, but what we've done is we've solved for them. The theta and phi functions actually have the same form as they did for the rigid rotor. They are these spherical harmonic functions. And they are important in describing where the electron is, but don't have any impact on its energy. To finally solve this equation, we need to apply a boundary condition that says these radial functions go to 0 as r goes to infinity, or that they're normalizable. And when we do this, we get radial functions that depend on two quantum numbers, of course, this principal quantum number n, and then we see L is also impacting this as well. So they also depend on the quantum number L. As always, I will show you the form for how you come up with these functions, but don't expect you to do that unless you are interested. Before we do that, however, let's go ahead and evaluate these functions and compare, as always, to the particle in a box. So we can see that the energy is equal to the following, and we would get this simply by evaluating the Schrödinger equation. So if we evaluated the Schrödinger equation for the 1s orbital function that we'll see in the next slide or two, we would end up with either one of these expressions here. They are equivalent. There's this additional constant a naught, that's the Bohr radius, that's made up of all these other constants, so these two are equal to each other. And we get actually the same solution that Bohr did. Remember, this here is Bohr's solution for the energy levels of the hydrogen atom, and recall that they were correct. So using the Schrödinger equation, we can actually come up with the same solutions. And the solutions here are actually quite interesting. So we have a very interesting potential well, right? We have this Coulombic attractive force as our potential well, but the shape of our solutions is actually pretty similar to the particle in a box. The lowest energy levels of 1, we see 0 nodes. As we increase, we get 1 node, 2 nodes, and so on. You recall this from Gen Chem when talking about nodes of these orbitals. And actually, interestingly, we have a different sort of quantization here where they get closer space as they get higher in energy. And that, of course, comes from the different problem. And there should be, sorry about this, there should actually be, let me go ahead and fix it, should be an equal sign there. So those two are equal. Now we have a whole bunch of quantum numbers, and you'll remember this relationship from Gen Chem. We have a quantum number n that goes from 1, 2, 3, 4 up in integer steps. We have a quantum number L that goes from 0, 1, 2, all the way to n minus 1. And then we have a quantum number m sub L that's equal to 0, plus or minus 1, plus or minus 2, and so forth, all the way to plus or minus L. Now, something that I'm telling you here is different from what you learned in Gen Chem. I am telling you here that the quantum number n is the only variable that determines the energy. So that means if we have a quantum number n is equal to 2, we should have the same energy level regardless of L and m sub L. And that should be somewhat disturbing to you because you know that things like the 2p orbital is higher in energy than the 2s orbital. And here I'm telling you that that shouldn't be the case. And it turns out that the reason you had this drilled into your brain is because that is true for every atom with more than one electron. So everything that's not the hydrogen atom will have that be the case, where the 2p orbitals are higher in energy than the 2s orbitals. But for hydrogen, n is the only quantum number that impacts the energy. So let's go ahead and look into the way we build up these functions. And here we can see it. And again, they are pretty nasty. So our radial distribution functions here are pretty similar to before. So we have a normalization constant, and this is dependent on the quantum numbers n and L. And then we have a polynomial here, or here rather. So this term is a polynomial term, and it's constructed in a relatively horrible way. And then we have an exponential decay term. We have some other r's as well here. So depending on the type of function that we have, we can build up our radial functions here. Our functions y of theta and phi, these are the exact same spherical harmonic functions as we have seen before. So if we can come up with our radial functions, we can multiply them by our spherical harmonic functions to get the total wave function for the hydrogen atom. Let's go ahead and look at some of these functions. On the left here, I have the radial functions. So here are the various radial functions for r, so 1, 0, 2, 0, 2, 1, and then all for the n equals 3. And if we want to see these in terms of the total wave function for the hydrogen atom, we need to put them in context of these spherical harmonic functions. So by simply multiplying these radial functions by the spherical harmonic functions that we've encountered before, we can come up with these equations. Note that just like for the rigid rotor, these functions are complex if ML is not 0. And what we can do for this is, just like we've seen before, is take linear combinations of these things to build up real functions. And when we do this, we actually get to the orbitals. So this is done, the s orbitals here. I mean, if we go back a slide, these 0, 0s, these are the s orbitals. So here we have a function for the s orbital, a 3s orbital, 1s orbital, and 2s orbital. And here we can see the linear combinations that are generated as we make things like the p's and the d orbitals. So these mathematical equations here actually represent our orbitals. So we can figure out, where these orbitals are likely to be, where the electron is, and so forth, and we'll work with this more next time. I want to point out before we move on that we can look at these equations and actually determine where the nodes are. So let's look at a p orbital here, 3p orbital. We know that since it's a 3p orbital, there should be n minus 1 or 2 nodes. And we also are pretty familiar with this from Gen Chem, that this p orbital has one angular node, it should have one radial node. We can see that in the math here. So the radial node will come about when this term is equal to 0. And this term is going to be equal to 0, of course, when 6r over a naught is equal to r squared over a naught squared. We could set this equal to 0 and say when is 6r over a naught equal to r squared over a naught squared. And we can get a value for when this would equal 0, and that will be the distance of our radial node. This term here is an exponential decay, so it's never equal to 0. And then we have a cosine theta. We talked about that before, how theta is going to be 0 at pi over 2, which corresponds to the xy plane. So we can see that this 3pz orbital has a node in the xy plane, and it also has a node in the specific radius, which we understand should be the case for a 3p orbital from GenChem. So with this, I'll leave it here. And then next time, we're going to actually mathematically work with some of these functions and see what we can say about where the electron is in these various orbitals.